So we learned that if you giving you more, if you inject current, like an injection, or excitation, okay, it give you more, it says NMP. And the NMP cause the EFC increase, EFP decrease. Then it gives you delta EF. Then when delta EF larger than EG, the material start to provide gain. But how many injection will give you how many EF is something we haven't know yet. So the third part we're going to practice or to have an idea how many carrier density is required to achieve a population conversion. AKA we need to find a relation between the N and the real position of here. This comes from the last slide, so we're not going to repeat again. Why we start with the quantum well? Because the quantum well case it doesn't need a approximation. You can be solved directly. So let's consider if the EFC is already some way not more than your ground state. Then your integration, the total carrier density is also this is the density of state. This is the Fermi-Dirac distribution. We already know it's more than the EX0, so this integration is meaningful. And then we integrate from the band edge to the infinity. That will give you a total carrier density. Alright, so if it is higher than the second level, yeah, probably you need to integrate from the new edge here again and adding them up. So now I will just draw bigger. So okay, so this is the density of state, so on the wheel. So if the EF is here. Okay, so then you have something like this. This is the total carrier density from the ground state. But surely you can also calculate for another, but the amount will be much less because it's already much higher than the EF. So in summation, probably this doesn't count. Yeah. Since we are trying to calculate real number, in the perspective of the science for perspective, surely you should adding up all the contribution from each level of the density state. But while if you're trying to put the real number in, you will see the portion of the higher state is actually way much less than the contribution of the real one. So while you're calculating while you're trying to find the real position of EF, actually that will be better and better. But if you have two bands with very close band edge, for example, heavy hole and light hole, yeah, probably you need to calculate both. This is also part of your homework for here. We only one more for today, but the calculation needs some time. Alright, anyway. So this is the red integral. If we only consider the ground state, the contribution of the ground state, it is a constant. Then we have a direct relation between the carrier density and the position of Fermi level relevant to the ground state. Then do some rearrangement. EF could be written to the ground state plus kT times long exponential n divided by nc of the two-dimensional case minus 1. Alright, so this is the number we also arranged from last week. It's only most the function of its effective mass and its quantum wave width. For a material with a high effective mass, you also have effective high density of state. But if you really need to count the very many ones, then you need to calculate with a different En, but the same Fermi level, then adding up. But in this case, it will be easy to calculate N if I give you a yes. But if we need to calculate, I give you some N, you want to calculate where the EF is, it will be difficult. Yeah. So giving a position of EF is easy to calculate how many the carrier density is. But if I only give you a number of the carrier density, you need to do that properly graphically. It's also the homework you need to do. I will explain that while explaining. Anyway, but at the least, if we have only one band, the direction is mutual. There's an equation here. If I know where the EF is, I know where the carrier density in the conduction band. Or if I know how much the carrier density in the conduction band, surely I can calculate where the EF is relevant to its ground state. And the ground state can be calculated by we have done that in the lecture 1. So the 2D case is rather easy, so I will start with that. Okay, so here's the example. If we have again a 3 nanometer gallium arsenide. Yeah, I think I don't want to give you too many examples now. That will be easy for me to make mistake. But for the exam, I will give you another example. Surely I will do the gallium arsenide again. Okay, let's consider a 3 nano gallium arsenide sandwich between the powder outgas layer. And the outgas layer has a band gap of 1.62 eV and the gallium arsenide is 1.42 eV. And delta EC over delta EG is 0.36 and delta EV over delta EG is 0.34. The effective mass of the electron is 0.067, quite more. Okay, so let's consider if the pumping is hard enough. So the Fermi level, quasi-Fermi level for electron reached the EC of gallium arsenide. How many carriers it should have? First, we also still need to find the position even 1 yet. So the procedure is the same. We need to repeat the whole thing. What we do 1 week ago. Okay, so the E1 is 623 milli-electron volt above EC. And so we know where the EN1 is. Then according to the finding a mass, we sequentially find the ground state is 89.6 MeV above EC. So this is the case of the infinite quantum wave. We need this number to calculate the finite quantum wave case. Anyway, the finite quantum waves after the same procedure, we will find the is 89.6 millivolt above EC. Alright. So NC2D is the same. We just put the M star over E to be 0.667 and the D to be 3 nanometer. We get the NC2D is 2.41 times 10e18 per cubic centimeter per cubic centimeter. Okay, so we have the value here, we have NC2D, and we also have the position of the EF to EN, because the EF is at the position of EC, and the EN1 is 89.6 millivolt above it. So the EF minus the EN is minus 89.6 MeV. And the KT at the 300K is an easy number to remember. You don't need to calculate every time. The KT for 300K is 25.8 MeV. Yeah, usually I don't change the number. Usually, because it's meaningless to give you something like a 0K, and that just test you if you really watching the covalent clearly, but that doesn't give you any physical insight. So I usually just always assume the T to be 300K. Alright, so we can put it down, and the exponential is term plus 1, then it becomes, okay, not too much, only 0.03. So you only need to inject 7.23 times 10e16 per cubic centimeter carrier to let the EFC reach the edge of the conduction band. So you see, if the effective mass is high, the NC2D will also be higher. Then, in order to reach the same EF minus EN, you need also a higher carrier density of state. To let, if the EF minus EN is given, the same number, the necessarily excitation level will be proportional to the carrier, to the effective density of state. Is also proportional to the effective mass. So the quality of the effective mass is not only relevant to the speed of the electrical conduction, it also relevant to the optical gain, or the maximum optical gain, or the required excitation level to achieve the population equilibrium. Like gallium arsenide, the effective mass is so small, it's only 0.067 times ME. But for gallium nitride, it's 0.2. So that will be definitely more difficult to excite the gallium nitride to the population inversion. But from the other side, you will also give a higher optical gain. We will repeat this idea probably on about 2 times more. Yeah, so you will hear it again and again, and you feel, oh, this is so natural. So you are not intimidated by such a thing. Okay. The more trickier part is the bulk semiconductor, because the integration don't have a specific expression. So we need to do the numerical approach. 因为做数值题，所以这个数值题是这一段的高考，所以第3堂课其实是数学课。Alright, so this is the density of the state, the 1/2 pi bar times 2n star divided by x bar powers 3/2, and this part is the integration. Because this integration doesn't have a specific solution. From the last class, because the EF is much lower than E, so this term is much larger than 1. So it can be approximated with a Boltzmann limit, since this part, the one in the denominator can be neglected. So we made a Boltzmann tail or Boltzmann distribution of the carrier. However, while we are doing the high excitation, that the EFC and the EFB might be closing to your emitting levels, then the assumption that E minus F over KT is larger than 1 is a big mistake. You cannot use that. So you cannot assume you use the common Boltzmann approximation to calculate the actual carrier density or find the real position of Fermi level with a given carrier density. Then we need to do numerical approximations. So it is the same. If you let the B to be EF divided by EC over KT, so this is a unit length parameter about the position of Fermi level. And Y is E over minus EC over KT, so it's also a unit length value about the position of your emitting level. Alright, so this is B is a relative position of Fermi level and Y is a relative position of your emitting level. So after some rearrangement, it's actually still very difficult to solve. It looks like this way. So lots of people trying to give you a more direct answer by many models. So this is mathematical model. But let's see how we use this table. First, this is approach. If I give you a position of Fermi level, you can evaluate how many carriers in the conduction band. First, we also calculate the position, calculate the B and the Y, normalize to KT first. Then, first the Boltzmann approximation, you can just write it down like this one. So if at the Boltzmann approximation, that means the case we do in the last week, the whole term is close to square root pi divided by 2 times exponential EF minus EC over KT. Yeah, that is the identical case we learned from the last week. And then we put it back, and pi over 2 will be eliminating with the coefficient here. So then it becomes NC exponential blah 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 blah. That's what we done this week. And this approximation has an acceptable range. How do he define the word acceptable? Acceptable means the actual value of the carrier density is error to your model is less than 1%. This is the definition. Yeah, surely you can define something called 0.1%. Then your life will be more difficult because the fitting will be more difficult. So this is only a value. That means if what does this model applies and the error to the real answer is less than 1%. That means the B is less than minus 0.5. B less than minus 0.5. That means, okay, so I will write it down here. B is equal to EF minus EC over KT. So B less than minus 3.5 means EF is less than EC minus 3.5 KT. That means if this is your band, and this is your EF, and this is DC. The EF must be less than 3.5 kT below your band edge. Then the Boltzmann approximation stands solid with an error less than 1%. However, if not, for example, your Fermi level is already on DC. If you still use the Boltzmann distribution, the error will increase. For example, this is if V is equal to 0, and the black curve is the solution. We do that one by one, so you can regard it as the real solution. And the Boltzmann equation is this curve, dash the curve. So when the V is small, or when the EF is far below your band edge, Boltzmann distribution is a good approximation. However, as the carrier density increases, the EF increases. Then the Boltzmann equation will overestimate the real carrier contribution. Since the dashed line is the carrier distribution you obtain the Boltzmann distribution, but the real one is the black solid curve. So that will overestimate the carrier concentration you have in the conduction band. Then you need to find another model. So below are some possible useful models. Let's go a more extreme case called the Sommerfeld approximation. If you took a Professor Science Day Physics, there's a chapter called the free electron in metals, and the quantum and the version is called the Sommerfeld model. It's the same Sommerfeld. So Sommerfeld approximation, it can be written something like this. It is 2/3 times power B times power 3/2. And if you really write it down with only first order, the expression is exactly like a metal. This is the statistic of metal. So it only happens when the excitation is so high, so that the carrier concentration in the semiconductor is just like metal. This also don't really happens in the usual case. Yeah, we don't pump the semiconductor that hard. It's only something like we are trying to eliminate the boundary between the same metal and the semiconductor. If the excitation is so high, so the carrier density is as high as you have in the metal, then your statistic merge to the Sommerfeld statistic. Okay, so what is important is something in between. So for Sommerfeld model, it is only correct when the mu is larger than 11. That means the EF is already in the middle of your band. Yeah, that's also the definition of metal too. And how high it should be? It should be higher than 11 kT. Then your band edge. Then your statistic will have a less than 1% error than the real case. This is also extreme. For most of the semiconductor lasers, we only wanted the light near the band edge to lace. So it's the most tricky part. That means the mu is around 0. Yeah, usually larger than 0. So you might need to adopt the right one to find the relevant case. For example, if your mu is 0, just like the previous case, if the mu actually just touch the band edge, then that means the mu is 0. So we just need to find one that might apply. Less than 0.27 no. Okay, this is probably okay. So we can take something called under approximation with second order. With second order, that means you need to calculate the f over 1, 2 with half of pi times e. And what is c? We have a z here. Okay, z is here. Z is 1 plus mu. So you calculate the z first. Then the second order, that means you only do with the A1 and the A2. So it's an approximation. That means in this case, for example, b is 0. When b is 0, exponential b is 1, right? So z is log 2. Log 2. Then f of this Fermi-Dirac integral can be approximated as square root pi divided by 2 times log 2 times a1 equal to 1. So this is only the first order. And the a2 is 0.146 times log 2. Okay, so now you have the approximation, a better approximation of the Fermi-Dirac integral. Then insert back to here with the NC you have. Since 2 over pi can be divided by here, so you can already put it back. You don't need to calculate the power of the square root over 2. You only need to calculate this polynomial. And the times is effective density of state. Then you get one number which shows as less than 1% error. Okay, so this is the example here we have. Alright. So this is if consider the bulk of getting arsenide is optically pumped. It's pumping by a strong line anyway. And the possible ratio of the EC of gallium arsenide. How many the carrier density should have? Alright, so first we find that V is equal to 0. Then we can only use the second order under approximation because it fits its criteria. Then A1 is 1, A2 is 0.146, and the F of 1 over 2 is pi over half Z times, and the Z is log 2. So since you are doing some calculation, you can just give a number. Alright, and this is NC. This is the effective density state. 4.35 times 10^17. Then just find it, put it back with the same order. Yeah, since the 2 over square root pi and pi over square root can be eliminated, so I didn't really come to that. So you only need to calculate the density of state times this one plus second order, and this is your final answer. So it's actually pretty straightforward. You only need to know which model is the one we should pick. So let's compare the two cases. In this case, we need that if we wanted the E to be aligned to EC, the carrier density we calculated the 3.3 times E17 cm minus 3. And in the previous case, we do the quantum wave case, we also assume the EFC matches the edge of EC. Then our answer is 7.23 times E16 per centimeter square, which is lower than that. Can anyone have a very direct explanation why the with the same Fermi level position, the carrier density will be lower in the quantum wheel case。对，这里有4。好，恭喜。对，因为那个量子井它的那个空间小嘛，你想想看，这个是 energy， 然后呢，对于 Bach 在这里有这一条是 parabolic， 但对于光灯位而言，它是一个阶梯状的，但它永远不会超出 Bach 的 tensor， 因为它其实它的量很小了吧，它能够忍受的 state 本来就比 Bach 还要少，所以它 tensor state。所以我在一样的 Fermi level 的时候，我整个积分出来的面积自然是比较低的。对，因为我的一样的 DOS， 一样的 EFC， 那我只是通常做积分，那一个比较高的东西乘一个 probability， 可以让它那个 density of state 比较低的东西，它的那个 pumping 的需要的载值的浓度